Hello, here's another couple of practice questions for astronomy and cosmology, starting with, in the universe, there are about 10 to the 11 galaxies. Each are about 10 to the 11 stars, with each star having a mass of about 10 to the 30 kilograms. So big numbers. Estimate the attractive gravitational force between two galaxies separated by a distance of 4 times 10 to the 22. I don't know why they had to put a 4 in, seeing as they're just making up that number. They could have any separation if they wanted. It just makes our maths a little bit more involved, but it doesn't make too much difference. These are all estimates, and we're estimating a gravitational force, so we've only really got Newton's law of universal gravitation to go with. Our GMM over R squared. G is 6.67 times 10 to the minus 11. At least that's bringing down some of the mega mass that we've got on the numerator. So what is our mega mass? They're both considered to be the same thing. We don't even care about how many galaxies there are. It's 10 to 11 because we're just dealing with two of them. So we got 10 to the 11 stars with 10 to the 30 kilograms in each, and then we're squaring because we've got two m's, treating the galaxies to be the same as each other. And then we got R squared on the bottom, the annoying 4, although the G is making things annoying anyway, times 10 to the 22, and then we've got to square that as well. So let's deal with a whole load of tens on all this then. So at the top, we've got 41, 82, minus 11, so 71 on the top, 10 to the 71. Then we've got 10 to the 44 on the bottom. And then for numbers, 6.67 divided by 16, it just makes it a bit easier sticking all this in the calculator. So, and that's going to be what, 27 that we've got here. If we replace all of these tens, save a bit of space, I'll just make that 10 to the 27. Putting this into the calculator, we're going to have 4.2 times 10 to the 26 newtons. Two significant figures. Okay, right, I've already taken up a lot of space on that one. Explain why the galaxies do not collapse on each other. Well, we got a number of things we can pick. So let's say, well, we got the expansion of the universe, so we could say the universe is expanding, which is going to be taking them apart. And we can apply any of our Hubble's law ideas to objects that are not in the same galaxy. So we've got universes expanding. We got force from other galaxies. You know, they've told us that there are 10 to 11 galaxies here. So we got force from other galaxies pulling in other directions. They're the two that mainly spring to mind. I mean, the other thing as well, I suppose, is you've got this. Okay, so it's a large force, but we've got a very, very large mass and a very large separation. So even with a force in the order of 10 to the 26 newtons, I mean, look at the mass we got on these things. Even if you were doing a F equals ma sort of, you know, finger in the air calculation on this, then you're dividing this force by a 10 to the 41. That's not much of an acceleration you're really getting out of this. I mean, I know this is all approximations, but you could have that thing as well. Say it's going to be a small acceleration. So that's three options that you've got here for why they don't collapse on each other. C, describe qualitatively, always a difficult one to say, the evolution of the universe immediately after the Big Bang to the present day. You are not expected to state times, good, for the various stages of the evolution. Right, again, people sometimes leave stuff out of these descriptions because it can seem maybe a little obvious, some of the statements that you get marks for. You don't need to include absolutely everything, but the idea with the evolution of the universe is it is starting small and hot, is expanding to become big and cool, and the more it cools, the bigger the objects that can form. So this is the pattern that we're wanting to go through here, are the key points that you're going to want to turn into sentences. So we can start with the early universe was very hot and dense. Very hot and dense. So that's just stating what we're starting from. We could say that the forces are unified. That's something that you can slip in. But again, don't worry if you don't put in things like that. You can get the full marks on these sort of questions just by talking about what's actually happening to the universe, really. So we can say universe expands and cools. And then we start forming things. So we can then say, we're working up in size. So we start off with quarks and leptons form. So start with the smallest thing. Then we can say expansion and cooling continues, and cooling continues. Then we start getting next thing up. So we're going to start getting protons, neutrons, hadrons. So protons, neutrons, so that'll be next. Then we're going to start getting nuclei, larger nuclei. Then the next one would be, so these are just separate points that you're expanding into sentences. But you can see we've got the same thing. You don't have to keep on saying expand and cool, but this is the process, isn't it? It expands, it cools, we get the next thing. The next one will be helium nuclei. That will be next. Then we're going to get atoms. Then we can put in, going to make quite a big jump from atoms here. We don't have to go through, and then a molecule forms, and then a little bit of whatever forms. We're just going to say about, let's get up to stars and galaxy level. So let's mention fluctuations in density lead to gravitational variations. So that's something which is very useful because that's explaining how we're getting enough clumping for stars and galaxies. Stars and galaxies form. So, okay, we've made a bit of a jump going from atoms all the way up to stars and galaxies, but we've made our point. Expand and cool, the more we're doing this, the more it's cooling down, the more we can get stuff clumping together. If everything's got too much energy, nothing's really sticky. So yeah, we've got that. Then up to the present day, that's really taken us. Let's mention the background radiation. That's probably something we could say. Now universe has cooled to about 2.7 Kelvin. And 2.7 Kelvin, and then say we've got the cosmic microwave background radiation. So mentioning that. So it's just that pattern really, providing you get that pattern in. Starts hot and dense, expands and cools, next largest thing forms, expand and cool, next largest thing, etc., etc. So we're just doing that with the little kickers of this fluctuations in density is a nice little touch to add. So that's that. Then we've got D. We got some absorption spectral lines of the spectrum of calcium as observed from a source on the Earth, so like the lab source on the Earth, and from a distant galaxy. So this is our lab observation at the top, distant galaxy at the bottom, and we can see the wavelength has increased. So we've got a redshift going on here, which is what you'd expect. That's what Hubble's law is telling us. So describe an absorption spectrum. So again, we don't need a lot. So an absorption spectrum they are dark lines superimposed on a background continuous spectrum. Superimposed on a background or against a background continuum spectrum. I suppose you don't always get not every spectrum that you're looking at. So if you look at an emission line spectrum, you don't need the background in order to have an emission line. You could just have something which is being emitted at a particular wavelength. But if you've got an absorption spectrum, you have to have a background, otherwise there isn't anything to be absorbed. There has to be a dark bit in the spectrum. You can have emission line spectrums where you've just got flat and some lines coming up. If you've got an absorption line, you need a continuum which is already at a certain intensity, so you can have dark lines imposed against it. So you need to have the background continuum spectrum mentioned on an absorption spectrum, otherwise it just can't exist. Then we get the last part of the question. Use figure 10.1 to calculate the distance of the galaxy in megaparsecs, and they've given us a fairly low value of the Hubble constant, but that's fine. So we go to our Doppler equation. So our V over C is our percentage change, our fractional change in the wavelength. And we know from our Hubble's law that V is H0D. So that's where we're getting Hubble's constant in this. So we want to get our change in the, we want to get D, sorry, we want to get the distance of the galaxy. So we've got the D is going to be equal to C times delta lambda over lambda times the Hubble constant. Our delta lambda that we've got from here is, it's this bit here. So we've got our, we got 80 plus 6.6, so 86.6. And if we just keep everything in nanometers, then we'll be fine. Make sure you don't get messed up on C, the usual thing with Hubble's constant, we want it in kilometers per second. So 3 times 10 to the 5 for our speed of light. We've got our change in the wavelength, 86.6. We've got then our original wavelength. So this is what we see in the lab. You need to make sure you pick up the right number here. The one here from the galaxy, this is what has been changed. This is our reference. Our reference wavelength is the one that we're getting from the lab, the one that we're observing from a source on the Earth. So we need the 393.4, not the 480. And then we need to multiply by 50. And this will come out in megaparsecs because we're cancelling the kilometers per second in the Hubble constant with our speed of light, and then we've got the 1 over megaparsecs. So we're just tapping all of this in. This is giving 1321, which is 1300 megaparsecs, although actually they've given us more accuracy on this, but not on Hubble constant. Okay, we got high accuracy on these, surprise, surprise, but this, you can't start going nuts on accuracy of your answer if you're using Hubble constant, because Hubble constant isn't particularly accurate. So I'm going to stick with 2 significant figures there. So there we go. So that was the calculation at the end. That was a meaty question, that one. That was pleasing. Okay, I'll do one more. We've got describe briefly the sequence of events which occur in the formation of a star such as our sun from interstellar dust and gas clouds. Right, so it's got some similarities with the description that we give for the evolution of the universe, actually, but in the opposite direction. So we're going, rather than what we had for the universe, where we're starting hot and we're expanding and it's cooling down, here we're starting cool and we're contracting and it's heating up. So it's the same sort of thing, but in reverse. So what are we going to say with all of this then? We'll go with, so we start in here. We're starting from interstellar dust and gas clouds. So we can say that the dust and gas cloud, or clouds as they've put it, so taking what they got in the question, collapses, or you could say contracts, either one of them, contracts due to gravity. Then let's talk about the energy then. If this is what is happening, this is a process driven by forces, so it's going to change energy. So we want to say that the gravitational potential energy goes down, the kinetic energy goes up, so the temperature goes up. This is what's happening in collapse. Then we can say we've got a fusion. Eventually temperature is going to get hot enough and for fusion to start, nuclear fusion. So this continues until the temperature is hot enough, is high enough for nuclear fusion to begin. Fusion to begin. Then we're getting an energy release. So this leads to an energy release. And we need to say how we end up with a stable star, because we've got this collapse contraction, which is what we've set up here. So we then can say that a stable star is formed when we've got the inward force due to gravity. So this is our gravity is equal to the outward force. And the outward force is going to be things like thermal pressure, so our thermal motion, so let's say thermal pressure, radiation pressure, things like that. So yeah, putting those in. And then we've got something that's stable. So the kicking off our nuclear fusion is going to be enough to stop the contraction. And I mean, obviously the contraction would stop anyway. Eventually you're going to get enough outward forces going on, but the nuclear fusion is contributing to that. So yeah, that's how it's set up really. We're just going through those steps again. You're contracting, you've got energy transfer from one star or another, then energy release from fusion, and then we've got a stable star. So that is part A. Part B, figure 8.1 shows the evolution of a star similar to our sun on a graph of intensity of emitted radiation against temperature. Okay, right, so this is a sort of cut down version and backwards version of an HR diagram. Now remember, on the Hertzsprung-Russell diagram we normally have temperature going the other way. So they've changed things around here, which is why the white dwarf has ended up on the bottom right rather than the bottom left. But, you know, similarities anyway. The final evolutionary stage of the star is a white dwarf. Describe some of the characteristics of a white dwarf. Right, again, it's just some, so you don't have to be completely thorough and complete on every single property here. But let's say it is extremely dense. I mean, it really is. I mean, these are where you're looking at tens of kilometers across for these white dwarfs. I mean, these are the cores of these red giant stars after they've become planetary nebulae. So we've got, they're extremely dense. They are very hot. We can see here, this is straight off of the graph, that they're very hot. They've given that to us. We can say that there is no nuclear fusion going on. I mean, they're hot because they're, where the nuclear fusion was going on, and there's still a lot of residual heat there, but there isn't any nuclear fusion. They are supported against gravitational collapse by electron degeneracy pressure. Gravitational collapse by electron degeneracy pressure. I mean, that will do. You wouldn't even need those four. Usually these are like 2 marker things. So, but however many marks they want, you can pick out 2 or 3 of these. So that will do on that. Explain why in its evolution the star is brightest when it's coolest. So when it's coolest, so why is the red giant brighter than the white dwarf? Right, so let's look at brightness. That's our luminosity. So our luminosity, we can go to our Stefan Boltzmann on this. So we've got 4 pi r squared, Stefan Boltzmann constant, t to the 4. So, okay, the temperature is a major factor because the temperature is taken to the power of 4, but the radius, we got radius squared. We've got a surface area going on here. And yeah, this is just huge. The difference in radius between a red giant and a white dwarf, the multiplier is just massive. So we can say that the red giant has a much larger surface area, than the white dwarf. And this is dominant. This is dominant compared to the t to the 4 term. So yeah, if you work out the difference, the ratio of the surface areas of the red giant to the white dwarf, that will have more of an influence than the ratio of these powers, these temperatures. I mean, you can see, okay, here it looks like we've got about, I don't know, about double the temperature. So that does make a significant difference. But that's a 16 times difference, say, in terms of the temperature of that multiple that we've got there. But the surface area of the red giant is more than 16 times the surface area of the white dwarf. So that could be another way that you'd phrase it on here. You could even start quantifying it, put in, this is around 16 times, maybe a little bit more based on this graph, maybe 20, even if it was 25 times. And then saying that surface area has more of an effect. So there you go, as a quick one. Again, a nice little descriptive one to actually put alongside the previous question. So you get a lot of these descriptive questions in the astronomy section because there are only so many calculations we've actually got. Well, we've got luminosity, we've got Doppler effect, we've got Hubble's law. I mean, that's kind of pushing it. I know they sometimes bring in, we had on the last one, Newton's law of gravitation, but they're not exactly calculation heavy, these questions. So yeah, it's good practice for writing out some descriptive stuff.